Welcome to this presentation about theory and computation of substructure characteristic modes. My name is Gustafsson, and this is joint work with Lukas, Miloslav, Johan, and Kurt. So characteristic modes are popular in antenna design and analysis. A scattering formulation was introduced by Garbage and a method of moments formulation by Harrington and Mounts, both more than 50 years ago. The substructure characteristic modes are important for cases involving ground planes and other backgrounds. And the method of moments formulation is based on block matrices and ensured complement. In this work, we present the scattering formulation for substructure characteristic modes. And the scattering theory is developed for arbitrary-shaped regions, materials, and backgrounds. It can be used in arbitrary full-wave solvers, for example, method of moments, finite element, and FDTD. And we also provide code so you can actually try it yourself. So the characteristic mode substructures is based on dividing the region into two different parts. One is the design region or controllable region, and one is the background region. This decomposition of the region induces a decomposition of the method of moments matrix. And elimination now of the induced currents in the background reduce the size of this method of moments matrix. That is the one that we can see down here using this short complement. And now forming the traditional characteristic modes from this reduced matrix defines the substructure characteristic modes as these eigenvalue problems that we have down here. One example is illustrated to the right here with a kind of a simple model with the ground plane as a background and a region here as a substructure. And here you can see the modal significance plotted. The dots comes from this impedance formulation that we had here, and the lines from the scattering formulation that I will present next. And as you can see, they produce the same results for these cases. So the scattering formulation is formulated in a completely different way. So here we formulate scattering matrices. The first one is formulated from the background. So here we have some illumination A, we have some outgoing waves S, and the map between those ones is a scattering matrix SB. Then there is a second scattering matrix S, which comes from the complete region in these cases. And as introduced in the papers that we can see here, we can actually do an eigenvalue problems with these scattering matrices. This is this generalized eigenvalue problem here. And this computes the scattering eigenvalues and also the excitations. And what we can show is that the scattering eigenvalues for this are linked to the previous method of moment substructure characteristic modes we presented on the previous slide with this simple transformation that we have. So what this does and what we do in the paper is that, of course, we present the mathematical derivation where we actually prove that these are the same. And we also provide many numerical illustrations. See some of them here. They involve ground planes, both metallic and dielectrics. You can see another complicated here with the larger ground plane. And we compare them and actually show that they are the same. And as I mentioned, now we can actually do this in an arbitrary full wave solver. We also present an iterative algorithm that you can do this quite efficiently. So in the paper, we contribute to the theory of the characteristic modes. So in these cases, we actually develop quite a lot, and especially the scattering formulation here. And particularly by introducing what is the substructure characteristic modes from a scattering perspective, and actually proving that it's the same as the traditional one from the impedance ones. And this is some ongoing work over the last couple of years. We presented quite a lot of results, which deepens understanding of characteristic modes by seeing them from a scattering formulation, which also make them independent of the solvers. Now you can do it in whatever solver you would like. So I hope you will enjoy reading the paper, and I thank you for your attention.